Do we have Jack? Yeah. Okay. So we see Jack, we see your slides. Yeah, good to go. Thank you very much.
Let me just check if you can see my laser pointer. Do you see that?
Yes, definitely, yeah.
Okay. So again, like the other speakers, let me start by thanking organizers and apologizing for not being able to attend. It would be wonderful to be there, and I've been enjoying the talks remotely. So what I'm going to be telling you about today is sort of a, let's see, hide floating heating controls. There we go. Is not what we intended to do. I'm going to pretend that the experiment I'm describing to you was sort of planned all along, but this is not the case, and you'll probably be able to tell. What we ended up building is a very harmonic oscillator, something that is just really a harmonic oscillator at the quantum level, and I'll explain what I mean by that. And it remains so even when we drive it to very large amplitude of motion. So that's sort of what this talk, this title is, and this title is what we try to do with such a system. Okay, so I will begin by saying a little bit about macroscopic quantum phenomena. Obviously, the audience is full of experts, but I'll just tell you very briefly my perspective. I will present a sort of advertisement for why superfluid helium is a really amazing material for doing experiments like this. And then, again, explain why it is that a very simple harmonic oscillator can test interesting things about possible corrections to the Schrödinger equation. So let me start by thanking the folks who do this group, our collaborator Jakob Reichel in Paris. I particularly want to mention research scientist Yogesh Patel, who really helped to lead this project. Okay, let's see. Okay, so I think there are a lot of different reasons to study quantum mechanics on a large scale. First is just, it's amazing. Intellectual curiosity is what you could call it. But to me, I never cease to be amazed by, for example, Marcus Arndt's group ability to take things that look like this and launch them through meters of vacuum and have them pass through real physical slits, like one of those drawings that Niels Bohr would do during his debates with Einstein, and collect those molecules and see them arrive one by one, but the overall pattern revealing the interference of the de Broglie wave associated with this thing's center of mass. And while Marcus was speaking this morning, without his permission, I took a screenshot of this results just to say, like, it keeps going, it keeps getting better. And if that's all that we're doing to make things like this better and better, that would be very much worthwhile. At the same time, motion and mechanical systems are very robust classical technology. They are in your cell phone. They're making your calls possible. They're in astronomical instruments. They're in all kinds of very delicate systems. And by and large, if you can take a robust classical technology and bring it into the quantum regime, there are advantages to be had. But the main focus, I guess, of this conference and my talk is that there's a possibility that there will just be genuine surprises. There will be ways in which quantum mechanics does not accurately describe sufficiently macroscopic entities. And we've heard about the ideas of gravitational decoherence, or the idea that space-time is simply classical. The idea that I'll be talking about mostly is that physics like this can manifest itself in small corrections to the usual Schrödinger equation. And there's this very nice cartoon which illustrates one notion about this, which is that at some very tiny length scale, like the Planck length scale, something about space-time is quantum mechanical and not well understood. And it's a question of, how far do you have to zoom out before you lose all sign of nonlinearities or corrections that this kind of microscopic phenomena would introduce to, somewhat larger objects. And in particular, what I will talk about is experiments in our lab that we interpret as giving a limit, a bound on the length scale at which nonlinear terms are present in the Schrödinger equation of being about 10 to the minus 19 meters. And there's a star here because I'll explain to you, sort of how we can interpret our data this way, but there are definitely different perspectives you could take on this. Okay, so we're talking about searching for unknown physics. Nobody has come to us and here's the complete theory of quantum gravity. Please go look for this effect. We're looking for unknown physics or partially understood physics. And there are a lot of situations in which people are in that position, like our our particle theory colleagues, for example. And so often this search for new physics proceeds in the following way. This is not the only way to view things, but this is maybe a helpful illustration. You have some known physics, like Newtonian gravitation, and for various general reasons, you imagine that there's a likely form for a deviation from this potential. And that form is motivated by some deep ideas, and that correction is going to have some specific parameters. In this case, it's capital R is going to be a length scale of this Yukawa correction, and alpha is going to be its strength. And so you go out and you look, you measure the attractive force between lead balls or neutrons or stars or whatever, and that you agrees the known physics places bounds on these two. And I pasted this from a Review of Modern Physics article, but each of these curved lines and colored regions represent an environment that excluded some part of the phase space for modifications of this form. Talk about macroscopic quantum physics. I think that many of us have in our mind a picture that's kind of like that, which they're sort of unknown physics, but there are at least a couple interesting parameters by which we could parameterize them. One is how quantum is the phenomena we're seeing, and how macroscopic is the object that is exhibiting it. Now, unlike the Yukawa potential, these are not real parameters. These are not numbers with units. They're a little bit more conceptual. One way, though, that you can start to make this quantitative, and that some of the theories encourage us to think this way, is to label this axis, not in terms of something with real units, but let's just say what aspects of classical mechanics must we abandon given that we observe certain kinds of data. And for example, if you were to take a system in its ground state and find that it has no fluctuations whatsoever, this is consistent entirely with classical mechanics. If you find that once you've removed all of its energy, fluctuations, well, that's something that isn't predicted by classical mechanics. We have to give up a piece of classical mechanics. If you measure position and momentum distributions and find that your results are inconsistent with any underlying joint probability of those two variables, like in the first Fock state, that's another piece of classical mechanics that we have to give away. And then if you do sort of similar measurements on widely separated objects, and again find that there's no underlying joint probability distribution that would explain your measurements, you have to abandon still more of classical physics. So this is a hierarchy of more and more quantum phenomena. It's not the only way to put such a hierarchy together, but maybe it's just a helpful introduction. The other axis is sort of how big an object is doing this. And again, I would say that there is no unique metric for this. There's no completely model, independent notion of macroscopicity. Just very qualitative, you can make more sophisticated ones than this, but here's a very unsophisticated notion of macroscopicity, which is simply the mass of the object in question. But this is certainly one thing that seems macroscopic. Another would be sort of the physical extent of the motion they're talking about. If it were a superposition, maybe the length scale of the superposition. If it's just 0-point motion, maybe the physical scale of the 0-point motion could be femtometers or tens of femtometers. And so, for example, a system that exhibits fluctuations that classical mechanics says should not be there might be regarded as more macroscopic if those fluctuations are, say, on top of some high amplitude motion. This doesn't have to be your notion of macroscopic, but it's at least jives with our intuitive sense. If you paint this picture of two-dimensional parameter space and fill it up however you like, then specific models of beyond standard Schrodinger equation physics will make certain predictions. And every experiment that you do, so here's just a few of them, every experiment that you do in which your data agrees with regular quantum mechanics rules out some region of the space. If your experiments rule out enough, maybe one of these theories just is completely incompatible, or maybe you're just constraining some parameters that appear in this theory. And again, this is just a cartoon. There's nothing serious to be taking away from the shape of this curve or its extent or anything like that. Okay, so this is one way to think about searches for new physics. And in this talk, I will describe an object whose mass is on the nanogram scale and whose motion, even when it's on the order of 100 femtometers, we can still see quantum effects like this, zero-point motion, if you like, or vacuum fluctuations on top of the high amplitude motion. Other experiments would sit in different places on this graph. Okay, so with this sort of notion of a parameterized search for new physics, let me try and narrow down the kinds of models that an experiment that's in this regime of, say, a relatively massive object undergoing relatively large amplitude motion, but not exhibiting a very strong quantum effect. It's not exhibiting interference or obvious superposition or non-locality or anything like that. We're in this sort of regime of modest quantum mechanics at relatively large scales. And now we can ask, what class of corrections to quantum mechanics would this be, say, most interesting or able to test? And again, here I would just take a step back from jumping to any conclusions and just lay out the steps of reasoning, which is that no physical theory has proved to have an unlimited domain of accuracy. So quantum mechanics may be the same. We know that quantum mechanics is very good approximation in all the regimes that we've been studied it so far. So it's possible that this new physics could emerge as small additional terms, small corrections to this equation. There are an infinite number of possible corrections, but let me just draw your attention to three different broad classes. The first would be nonlinearity in the wave function. The Schrodinger equation is perfectly happy to have superpositions of solutions, but if there are nonlinear terms in the wave function, these superpositions do not last in the same way. So here's what such corrections would look like. Corrections like this, as my understanding, do arise naturally in some notions of quantum gravity. They've been discussed by lots of different authors. And I think that as an experimentalist, if you want to search for them, the biggest impact of these little terms will be in superposition states. There's always the possibility that the weird data that you see is because of, just something perfectly conventional in your experiment that you just didn't understand very well, that mimics, say, one of these. This happens all the time. This is one of the reasons that experiments are hard. So it helps, in order to avoid being fooled by this, to use sort of, well, let's say very high quality materials and well understood geometries and things like that, just sort of the usual good experiment stuff. Another way in which the real world might deviate from the Schrodinger equation is nonlinearity, but not nonlinearity in the wave function as considered here, but nonlinearity in the Schrodinger operator. And by the Schrodinger operator, I mean everything in this equation that involves a derivative with respect to a space-time coordinate. Okay, so here's the Schrodinger operator. Just pulled out the part of the equation in which you have derivatives with respect to space-time coordinates. This is an operator that just appears linearly in this equation, but we could imagine that, whatever the new physics is, it's manifest as additional corrections in this quantity. Notice that these extra powers of the Schrodinger operator leave the equation linear in the wave function. So this kind of perturbation doesn't sort of particularly strongly impact superpositions. Since these new terms would be related to derivatives with respect to space-time coordinates, maybe their existence would reflect something exotic about space-time. And as with nonlinearity in the wave function, there are underlying macroscopic relativistic quantum field theory ideas that do give rise to this. I will say I learned about this form of nonlinearity from papers by Belenkia and co-authors. And at this point, we're just sort of leaving it at math. There's a complete agnosticness as to the physics mechanism that might be producing these phenomena, but they make testable predictions. Like, you could do an experiment, and if your experiment agrees with the Schrodinger equation, you could say, hey, this epsilon is less than such and such. Or you could do an experiment over here. And if your data agree with the Schrodinger equation, that would tell you that epsilon is less than something. Okay. Now let me start to make some guesses about what a physical interpretation of this epsilon could be. The first is that this epsilon has some units, and those units could be written in the following way. Since it's involving things like kinetic energies, maybe it has h bar squared in it. Since it's the equation of motion for some object of mass m, maybe the mass units reflect the object's mass. And if you incorporate these two things, then you're left with something of units length squared. This is only one possible interpretation. So that's listed here. If this length scale is maybe taken to be, again, not specific to the object under consideration, but some fundamental constant that appears in our fundamental equations of motion, then this new constant has units of length, and it's a length that quantifies the scale over which wave functions evolve nonlinearly. So these are sort of the mathematical structure, the physical idea that might underlie such terms. And then if we want to look for them, what kinds of experiments are most sensitive to these nonlinearities? Well, if you want to make your little correction big, you should be thinking about a big object, a heavy object with mass m, really cares about its mass. And then you're talking about higher powers of derivatives with respect to spacetime. So you'd like a wave function that, let's say, varies very rapidly with space and time. Okay, and so you get that to some extent from large mass, but also from large amplitude motion. Okay, that gives you big values of these things that are going to appear nonlinearly in the corrections. So these are nonlinearities that are particularly sensitive to high amplitude motion of heavy objects. They don't particularly require superposition. If you sort of take this seriously and ask what kind of constraints exist at this point, my understanding is that the best such constraint is from scattering measurements at the LHC, and it says that if there's any length scale like this, it's less than 10 to the minus 19 meters. So that's the present state of the art on nonlinearities of this form with this interpretation. And by the way, this I'm going to be focusing on for my talk. Okay, so the experiment that we do is cavity optomechanics, and we're particularly going to try to access those nonlinearities by doing cavity optomechanics with single phonon counting technology. So since this is an important part of the talk, let me, oops, sorry. This is an important part of the talk. Let me just remind you a bit how cavity optomechanics works. The idea is you have a high finesse cavity, laser light comes in, it goes out. There's nothing exotic here. If that back mirror is itself a mechanical oscillator, then it can wiggle back and forth. And even classical mechanics will tell you that the Doppler shifting of the light will produce phase modulation sidebands on your light. There's no quantum mechanics here. Quantum mechanics could appear if I put a detector here that goes click with the arrival of each photon. Because with each click, I'm entitled to ask, did this click come from a blue shifted photon or a red shifted photon? If I can find that out, then I know, let's say a click came from the red photon, that means I know that exactly h bar omega m of energy was deposited in this oscillator, and so exactly one phonon was added to this oscillator. And if I get a click from a blue photon, I know that exactly one phonon was extracted from this oscillator. So that would give us a lot of information about sort of the evolution of the quantum state of this system. In practice, it's really hard because you only get about one sideband photon for every 100 million unshifted boring photon. So you really have to be able to discriminate between them very effectively. The approach that we use has been used in many labs. It's just brute force filtering to pass one of these sidebands. The idea being that now when you get a click here, the back action through this modes that have been restructured by the presence of this cavity sort of adds or subtracts exactly one phonon from this mechanical oscillator. So this kind of setup has been implemented in many labs around the world. Our setup is a little different in how it's realized and various other things. The cavity consists of mirrors that are formed on the end faces of optical fibers. These are made for us by Jakob Reichel in Paris. We make the cavity by pointing two of these fibers at each other, and then you get a little standing light wave inside of here. That optical mode is pretty well coupled to the traveling light wave in the fibers, which makes this device relatively convenient to use in a cryostat. That's it. That's sort of all that goes into it. They're that easy to make. So we typically make a bunch of them, put them in a can, and bolt it to a dilution refrigerator. That's the optical cavity. For mechanics, we simply fill this space with liquid helium. So if I go back to a cartoon version of this cavity, there's no mechanics here. Nothing really can move. Everything is very stiff. But then we fill it with superfluid helium. And the way that these, maybe I don't have it as an animation, but the way that these mirrors work is they confine optical modes like this, but they also confine acoustic modes. The density waves in the liquid helium are confined by those mirrors in exactly the same way. So you get a nice family of optical modes and a perfectly overlapping family of density modes. And I will just flip through this relatively quickly, but I'll just put it up and tell you that if you're doing quantum acoustics or even quantum optics, superfluid helium is a really amazing material. Has essentially zero optical absorption. I mean, let me just say zero optical absorption, has zero chemical impurities, it has zero structural defects. Every one of its properties, linear, nonlinear, is already known. It's a very good thermal conductor, and it's a superfluid. There are interesting things you can do with that. Building an optomechanical device in this way, we're left with an optical cavity whose finesse is about 100,000. The sound waves that are confined in here have quality factors also of about 100,000. And the mode volume, which is about 100 microns by 10 microns by 10 microns, is about 1 nanogram of matter is participating in this sound wave. So that's the device that I'll be telling you about. There's one other detail that is actually really important in these measurements, which is because the optical mode and acoustic mode are being confined by exactly the same mirrors, there's something very elegant when you calculate their overlap integrals. Basically, they're all zero. So here's an example of an optical standing wave and a density wave of helium. And if I ask how much is this optical mode detuned by this standing wave, the answer is zero. The overlap integral is identically zero. If I keep that same optical mode as shown here and ask, well, how much is it detuned by this sound wave? The answer is zero. You can just see this by symmetry or by the orthogonality of these sine functions. Same thing for this acoustic mode. When I get to this acoustic mode, in which the acoustic wavelength is exactly half the optical wavelength, then there is very nice overlap, very, very good overlap. But again, for all the other modes, none. And so that means that when light goes into the cavity, and the only time that a photon, a Stokes or anti-Stokes photon, an inelastically scattered photon will come out, is from scattering from this acoustic mode and only this acoustic mode. So another way of saying this is that every photon we get out that we know is a sideband came from exactly one mechanical mode. There's no mystery to come maybe from this one or maybe from this one. And that really simplifies a lot of our data taking. Can I just ask where we are in terms of time? How much time is left?
You still have 18 minutes.
15 minutes? Okay, good.
18, yeah.
18, forgot to start my, so that's very helpful. Okay, so that's the setup we have. It goes and lives inside of a dilution refrigerator. In practice, we shine a laser beam on it. The laser beam goes into the dilution refrigerator, hangs out the cavity, interacts with that sound wave, and comes back maybe with a sideband photon as well. Then it passes through 2 stages of filtering to block all of the original laser light and only pass the sideband photons to single photon counters. So here's the cavity that's here by the cryostat. Here's maybe our laser. Here's the motional sideband that would be created by a phonon creation event. I guess in this case, a phonon annihilation event. And then the filter cavities block this laser but pass the sideband to the detectors. And here's what the data really looks like. This is 1 second of data. And the blue is showing we spend 100 milliseconds locking all these cavities and lasers together, not taking data. And then we turn off all the locking stuff and just let the system sort of drift a bit for 100 milliseconds and record all the photon counts that arrive then. Each one of these red lines is a photon count. Then we relock and repeat. And these lines here, I just want to emphasize, when they actually arrive, they are an analog signal that is a spike whose timing we can identify down to sub-nanosecond resolution. So not only are we collecting photons and inferring the addition and subtraction of photons, we know exactly when they come to a very high degree of accuracy. So if we take this just for the arriving as a function of temperature, when the refrigerator is cold, we don't see so many counts. There just aren't that many photons in here to scatter off of. As the fridge gets hotter, we see more and more counts. And the whole time we see this persistent asymmetry. Sorry, the red data is taken with the laser here. The blue data is taken with the laser over here. And this persistent asymmetry between the two rates reflects sort of basic quantum mechanics of Gaussians under continuous weak measurements. But this is not like, in showing data this way, we have thrown away all the huge amount of information we get about the timing of every photon's arrival. So if instead we record those times and we go back and look at the records, here's time, red is when a photon was detected to have been found, and we take all this data and plot the two-photon correlation function, effectively the G2 function. Here's that data. The dashed line is a fit to what you would expect for sideband photons that are being created by an acoustic mode that is itself in thermal equilibrium. Doesn't matter what the temperature is. The temperature tells you sort of this, how many photons per second you're getting, but their correlation function is independent of temperature. And if you like this perfect exponential, tells us that we're really single mode as advertised, and that mode looks like it's in thermal equilibrium. We can go a bit further. In fact, we get so many clicks and store so much data that we can look at their 2-point correlations. When the laser is red detuned, here's the same data on a log scale. When the laser is blue detuned, same data on a log scale. But we can also look at triples of counts. And for every triple, there are 2 times between them. And so we can plot a histogram now of those 2 different times. Here's the delay between the first and second click, and the delay between the second and third. The points here are data. The surface is a fit, a 1-parameter fit. We can also, we have enough data to look at the 4-point correlations. 4-point correlation functions that there are 3 delays. So the data sort of in a cube, which is hard for me to show you. So I'm just showing you through that cube. And the data points get sparser when looking at higher order correlations. But here they are, again, with the fit through them. Again, this is a fit assuming that the acoustic mode is simply in thermal equilibrium. And so the fact that this data all agree very well tells us that our acoustic mode, that standing wave of sound, really is a sort of Gaussian thermal state. If you like, this is a measurement of that Gaussianity out to the 4th cumulant. And this is very boring physics, I think, for this audience. To be told that a harmonic oscillator is in a thermal state, like this is not very exciting. There's no quantum mechanics of interest there. Okay, so let me do another thing, which is also considered pretty boring, which is to take an oscillator that's in its ground state. I mean, we can tell that it's been cooled to about 1 phonon on average. Let me take that oscillator and then just apply a linear drive to it. Let me just drive it with a sine wave. And if you're a theorist, you know that what will happen is, you get a coherent state. As an experimentalist, though, we worry, we don't know a lot about this system. Our drive has phase noise. Maybe there are nonlinearities we're not aware of. Maybe, any number of bad things are happening. So we would like to confirm that when we apply a linear drive to this system whose equilibrium state has been very well characterized, do we really get a coherent state, or is there something that's not so simple? Again, let me admit that there's no quantum advantage or any real exotic phenomena associated with a coherent state, but it's a very useful state. all know that because we pay a lot of money to certain companies to provide us high-amplitude coherent states of light. In fact, here's their company. This is not, in fact, their slogan, but I think it makes a nice match to the single photon company. So look, if you're doing quantum optics or quantum acoustics, being able to generate very pure high-amplitude coherent states is really useful. In specific, in the case of acoustics, doing so to do acoustic interferometry, the standard quantum limit. That's interesting. What I'm going to talk about today is how one's ability to do that constrains the linearity of quantum mechanics. Okay, so in order to drive acoustic mode into a high amplitude coherent state, we use the exact same setup. We detect its motion in the exact same way. There's a laser that's detuned such that any motion will create sidebands that are resonant with gravity and with those filters, and they'll go to a single photon detector. To get the acoustic mode ringing, we also send in two lasers whose note is chosen to be near to the frequency of the acoustic mode to provide a near resonant drive, but otherwise not to affect the system very much. And then we just sort of vary the frequency of this beat note and count how many photons are produced as sidebands from this detection beam. And so here's the data measured in that way. This is the frequency of beat note. This is the rate of photon arrivals. And this is for different strengths of the beat note. This is just the resonance of a damped driven harmonic oscillator, except that maybe its motion is being read out in this very unusual way of collecting individual sideband photons. These resonances look nice. They look like nice linear things. If we fit them and extract their heights, then as we harder and harder, their amplitude increases in just the linear fashion we would expect. We can turn this amplitude of signal into a mean photon number, basically via that calibrations that we did measuring the thermally activated signal. So just long story short, we know not just that this is, out of photon, and this corresponds to a coherent state, or let's say a coherent state, a state in which the mean is about 8,000. Okay, so this acoustic mode seems like it's behaving linearly as we drive it up to large amplitude, but is it really maintaining its quantum purity? And the way that we can answer that is just the fact that when you drive the acoustic oscillator this hard and you record the arrival times of the photons, you end up with about 100 billion counts in one day of taking data. And so that's in fact what we do. We have this huge amount of photon counts, and that lets us do very good statistics. So again, let me explain what we're doing. We have characterized that in equilibrium, the acoustic mode is in a Gaussian state of a mean photon number about 1.5. We would like to drive it. We can tell that we're driving it to about 30,000 coherent photons. And what we're wondering is it get any bigger? Does it get stretched out? Is there any sign of something funny going on? And the way that we're going to characterize that is by looking at the two-point correlation function of the sideband photons. And here's that two-point correlation function. This is when we hardly drive the acoustic mode at all. There's only 1/20th of a phonon of coherent drive in there. So it looks very much just like the thermal state. Its G2 function goes up to 2. It hardly knows its displacement is much smaller than its quantum or thermal noise blob. And so the height of this feature is still about 1. We gain data driving the acoustic mode up to about 140 phonons. It looks exactly the same qualitatively, except that this thermal contribution is much, much smaller. Instead of being 1, order 1 over this number of phonons. It's not exactly that. There's a factor of 2 or something like that. But basically, what you expect is that if you take a thermal state like this and displace it more and more and more and more, if that's really all that happens, then the thermal part of your signature in G2 just scales down and down and down. Okay. So this is what that data looks like now with the 1 removed, the floor of this removed, plotted on a log scale as a function of time, where we're driving the acoustic mode to 0.1, 10, 1,000, or even 100,000 phonons on average. And these dashed lines are the fits to what you would just calculate for a perfectly nice displaced thermal state. The fits are pretty good. In order to quantify that, let me just zoom in on the zero delay time, the height of this feature here, as a function of how hard to drive it. And again, if you hardly drive it at all, that's 2. It's basically thermal. And the harder you drive it, the closer it gets to 1. The closer it gets to being like a coherent state. Again, the statistics in this data is so good. As we drive it so harder and harder, we collect so much data that I should really plot this on a log scale. And here's the data, now plotted on a log scale. And this curve here is just the fit of standard quantum mechanics for a displaced thermal state, and it fits extremely well. So again, this is another very boring result, right? I took a Gaussian state, a very cold Gaussian state. I drove it. I got a coherent state or something very, very close to it. As an experimentalist, this is nice. This tells us there's not too much parameter noise. The cavity isn't shaking in some very bad way. There's no sign of any nonlinearity. Eventually everything is a Duffing oscillator or whatever. Again, because in liquid helium, we know everything. We know what the acoustic nonlinearity is. We know what the electromagnetic nonlinearity is. We know all those things. We can calculate how big an effect they have this amount of motion. And the answer is, unmeasurably small still. Like the nonlinearity of the density in the helium. Like eventually at some point we would see that, but we shouldn't see it at this point. One way that I like to say this is that 10,000 phonons is a lot of phonons, but it's a very quiet sound in terms of like the amplitude of the wave. This is a very, very low amplitude wave. Okay, now let me come back to the first part of my talk and ask, does this agreement with quantum mechanics rule out anything that hasn't already been ruled out? Okay, we found agreement with quantum mechanics. Does that rule out any values of any parameters? Again, let me remind you that what I talked about was the particular kind of nonlinearity. Nonlinearity in the Schrödinger operator is particularly manifest in heavy objects that are moving a lot. That's kind of what we have here. And since we have sort of an unusually heavy object to be moving a lot and still showing what we would call zero-point motion or vacuum fluctuations, does that put any interesting constraints on this number, parameter that quantifies the strength of this nonlinearity? So in order to do that, let me now go back to my data and ask, well, what signal, how would this nonlinearity really manifest itself? Turns out to be relatively simple. If you have a driven oscillator evolving under usual quantum mechanics, the usual Schrödinger operator, this is what it does. But if you have, and your G2 data will look the way that I was describing. If you have, let's say, just the next correction due to something, an extra power of this Schrödinger operator, then the evolution of a driven state looks like this. It basically acquires a periodic squeezing. Okay. This is not so surprising. If this were a Kerr nonlinearity or something like that, it would get something qualitatively similar. So what we want to know is our data, to what extent does our data look like this and not like this? And so to make that more concrete, we calculate the G function for such a state. And basically it looks like just you would expect from the coherent state with this correction. If you like, the form of this correction is what you get from the periodic squeezing, and this epsilon here, the overall strength of it is the parameter. Sorry, this should be epsilons here. Okay, so what we do is we take our data, different drive strengths, and we just to this the parameter. And here's that data, here are those fits. Fits look pretty good. And as we take the data that say 130 phonons of drive, the value of epsilon that comes out from that is here. It's about -1 × 10⁻⁴. And in this data, because the data is at a higher amplitude, the fit is giving smaller error bars and smaller error bars. And when we look at the data that we drive really hard, like 40,000 phonons out here, the error bars on the value of epsilon that's returned is small. And it looks like the data is just sort of consistent with epsilon being 0. Let me zoom in here and just show you what the fitted value of epsilon looks as we drive the system harder and harder. Indeed, it is just getting smaller and smaller, with error bars approaching the part per million level. Okay, so that's sort of the main takeaway of this talk. We measure a relatively heavy object undergoing large amplitude motion, and at least its quantum fluctuations, the part that we can measure through the G2, look consistent with just regular old Schrodinger evolution. And more quantitatively, they rule out corrections like this to a level of what epsilon being 1 part per million. But epsilon, at least in the sort of story that's I learned about from Belenkia et al., has a meaning. It is connected to the length scale over which wave functions evolve nonlinearly. So any value of epsilon corresponds to a certain value of this nonlinearity length scale. Here, given the parameters of our system, I've converted this epsilon into the underlying length scale of new physics. And you can see that our data sort of is ruling it out at the level of 10 to the minus 19 meters. And in fact, if you ask just from a dimensionful point of view, why does this experiment access this length scale? The answer turns out to be very simple. We were talking about a wave function oscillating in a potential. The width of that wave function is the 0-point motion, which, like pretty much all of these optomechanical systems, is about a femtometer. And then our ability to sense any nonlinearity goes up. Our ability improves as the amplitude of motion gets bigger and bigger. So the reason that this data can probe 10 to the minus 19 meters is because we drive it to about 10,000 phonons. And I should just say that when we do a global fit to all of this data, with the only free parameter being L sub k, what we get is about 3 to the minus 19, at a value that's consistent with 0. And it's a value that's approaching the one returned by the LHC. So that is the end of my talk. Can you tell me, I think I'm at 30, or, maybe I'm at 0 minutes.
Yeah, I think you're at minus 1 minute.
Okay, so I will just put up my conclusions here, and thank you for listening. Sorry to delay your lunch, but I'd be happy to take questions if you like.
Yeah, thank you very much. So we have time for a short question. Let me start the other way now. Yeah.
Thank you. Very interesting talk.
Thank you.
I mean, I guess maybe you sort of said this, but I'm just curious how you isolate the system from extraneous vibration. I mean, I hear other talks where people worry about trucks driving down the street. So if you're looking for a single phonon, I mean, isn't this a challenge in setting this thing up?
This thing is pretty robust against that, and I will just tell you there's no heroic vibration isolation, and the reason is very simple. The reason goes back to this. Which acoustic mode does my optical mode talk to? It talks to the acoustic wave whose wavelength is exactly half that of the light wave. We like to do everything at 1550 nanometers just because it's easy. So 1550 nanometer light is going to talk to sound waves with a wavelength of 775 nanometers. Given the speed of sound in helium, this is 300 megahertz. And so 300 megahertz sound waves are not easily excited by environmental noise.
Okay, thank you. So I'm going to ask one other thing quickly. Are you going to stop at 10 to the minus 19, or are you going to push harder to get more tighter
We'll definitely
constraints?
push. This is like, we took this data just to sort of characterize our phonon counting apparatus, and then we had a lab move, and we had 2 students writing their theses, and sort of understood this paper from Belenkia a little bit better, and realized that our data could test this, and so we went through the data. So this was all sort of an accident. Yeah, we would like to retake this with an optimized device.
Yeah, Jack, I have 2 questions. So you have 300 megahertz. And sorry, are you saying that the optical mode is also 300 megahertz?
No, it's amazing how confusing people find this. The optical mode and the acoustic mode have the same wavelength.
Okay, good. I understand.
Yeah.
And sorry, you also said you're dealing with a large mass. What is the mass and how big is it?
About 1 nanogram.
So what is that
And
the mass of?
liquid helium.
Oh,
So
it's
the sound
helium.
wave
Okay.
involves a 100 micron by 10 micron by 10 micron blob of helium sort of doing this. So that's why I would say it's a nanogram.
Sorry, 1 nanogram?
Yeah.
1 nanogram. Thank you.
Okay, now there is a question in Zoom by
And
Anupan.
just to be clear, it's not the center of mass of that. Anupam, do you have a question?
Yeah, please speak up.
Yeah, thanks, Jack. Very nice talk. So I'm just a bit confused because you are saying that you're probing 10 raised to minus 19 meter, which is roughly 10 raised to minus 17 centimeter. It is roughly the length scale which LHC probes actually. So there must be some scale which is hiding in your calculation, which maybe I'm missing. So could you clarify this?
I'm not sure I understand the question. Can you say that again?
Yeah. So you mentioned that you are probing length scale, which is 10 raised to minus 19 meter.
Mm-hmm.
Now, this is roughly the length scale, LHC probes.
Mm-hmm.
And LHC is very high energy machine.
Mm-hmm.
And you are doing an experiment which is at low energy environment, very low energy. So there must be some other additional scale must be hiding in your calculation.
It's okay, so LHC probes 10 to the minus 19 meters, I think, because when you accelerate an electron or whatever up to 10 TeV, that's the de Broglie wavelength. Our mechanical oscillator has a de Broglie wavelength of almost that small. The electron gets such a short wavelength by going fast. Ours gets a short wavelength by being very massive, but not going very fast. So its 0-point motion is 10 to the minus 15 meters. Its de Broglie wavelength is 1 femtometer. And then the reason that we can get another 4 orders of magnitude is that we can average for a day and we can drive it to a high amplitude, and that gives us a couple orders of magnitude improvement. But yeah, if you want to know, like, dimensionally, like, why is it that number, 10 to the minus 19 or thereabout? It's because the 0-point motion, the extent of the wave function of an object like this, is 10 to the minus 15 meters. So even without any effort, you should expect to be probing some scales of a femtometer. Then we put it in some effort, and so we get another couple order of magnitude.
Oh, thanks.
Okay, so, okay, very quick question.
I think it's a follow-up to Anupam's question. I mean, when you said the linearity of space-time, is there an experimental measurement that you have in mind, this constraint from the LHC?
I do. This reference was on my slide. And I admit I don't really understand the analysis, but if you look in the paper from Belenkia et al., they mention this paper. That's what they cite as limiting their theory. I don't really understand how it works, except qualitatively smashing things together or with quantum mechanics, and you can say if there's going to be terms like this governing that physics, they better be smaller than 10 to the minus 19 meters.
Okay, so I think it's time to close this session. Let's thank Jack again.
Yeah, thank you. And I should say I'd be happy to take questions offline. If there's stuff you'd like to talk about further, just send me an email and we can arrange a time to talk.
Yeah, thank you. So we return at